Right, so good afternoon. It's my pleasure to introduce today's seminar speaker, Natalia Calvo, whom a lot of you already know. But Natalia first came to NCAR in 2002 as a visitor to work with me and others in WACM while she was getting her PhD at the University of Madrid. She then returned in 2005 after getting her PhD from the University of Madrid, did a postdoc through 2009, financed by the Spanish Ministry of something or other.
Of Science
and then she was an ASP fellow in 2010 and 2011. She returned to Spain in 2012 and became an assistant professor again at the University of Madrid, and she has been an NCAR affiliate scientist since last year. So Natalia is interested in both numerical modeling and analysis of observations, and her interests are in stratospheric dynamics, coupling with the troposphere and chemistry-climate interactions. And today she's going to talk to us about the 2015-2016 El Niño, which was one of the more unusual El Niños in recent memory. And Natalia, pleasure to have you here.
Thanks. I think mine is on now. Well, thank you for coming. I hope you find this talk interesting. And I'm going to present results from my PhD students, Maya Leniza and Froila Palmeiro. And we have done this work also together with my collaborators, David Barrio Pedro and Ricardo García Herrera, from the Department of Earth Physics in Madrid at the Complutense. So this strong El Niño in 2015-16 was the focus of the state of the climate in 2015. And actually this included several reports about this El Niño. And here on the right, you can see the Hofmöller diagram of the SST's anomalies in the tropical Pacific. You have longitude versus time. And you can have an idea of how strong was this event compared to previous events. And in fact, it was the third strongest on record. When I say on record, it means for the last 59 years, after the ones in 82, 83, and 97, 98. But you know also that this winter, 15-16, presented some other unusual features, and we had the earliest final warming of the last 3 decades that occurred on March the 6th. We also had enhanced precipitation over southern Europe, which in some regions exceeded the 95th percentile of the spring distributions. And this is actually what motivated the study, because we started to get a lot of rain in Madrid that spring, so we're wondering, maybe that is related to El Niño. So that's how the group started to get interested in this event. And then we also had exceptional Arctic ozone loss and the Cuvier disruption. And for ozone loss, I wanted to show you this plot that Doug gave me the other day from the NASA website, and it shows the evolution of column ozone in the polar region in red for the 2015-2016 winter, together with, in gray and black, the climatology for this period 1978 to 2015. So, well, the black curve is the mean, and then you have several percentiles and the maximum and minimum value. So you can see how for certain periods in the winter, sometimes in January and in February, we get values of column ozone that were lower than the minimum registered for the 1978-2015 period. But then in March, instead of low values of ozone, we get a large increase in ozone with large values there. So in fact, Mani and Lawrence in their paper in ACP 2016 said that temperatures in the Arctic lower stratosphere were at record lows from December 2015 through early February 2016, with an unprecedented period of temperatures below ice polar stratospheric cloud thresholds. And I will go back to this later, and I will try to explain this behavior in relation to the El Niño event. Then we had the Cuvier disruption that we see here in February 2016, when the downward propagation of the westerlies gets stalled, and then we have easterlies in the lower stratosphere. And there are a few papers that talk about this, but I haven't seen anyone that relates it to ENSO, so maybe that would be something to look at in the future. So as I said in the title of my talk, what I'm going to focus is on the El Niño event and the relationship with the impacts in on Europe and also with the final warming. So we know that El Niño events impact the northern hemisphere polar stratosphere and also surface climate through the stratosphere, especially in the northern Atlantic and European region. But that impact on surface climate in the European region depends largely on the type of El Niño event. And I'm sure you have heard about the different flavors of El Niño. So we are going to focus on the comparison between Eastern Pacific and Central Pacific El Niño. And this is because this 2015-2016 event was cataloged as an Eastern Pacific El Niño when one looks at the behavior of the SSTs in the tropics, in the tropical Pacific, but the event was the largest Central Pacific El Niño on record and exceeded by 0.3 standard deviations the previous largest Central Pacific El Niño event. So this characteristic makes this event a unique El Niño, and we will see how the response in the stratosphere is and how special it is. So to have everybody on the same page, I wasn't sure how much we all know about Central Pacific, Eastern Pacific El Niño, so I decided to include some slides about what are the impacts on the stratosphere and of both type of events. So I'm going to start with what we know as the canonical El Niño signal, that then we will see that is what is referred now as the Eastern Pacific El Niño. And in this schematic, I'm trying to summarize the responses that we see in the stratosphere and the main mechanism. So during an El Niño event, we have warmer sea surface temperatures in the tropical Pacific that generate wave trains into the extratropics and enhance the Aleutian low and the Pacific North American pattern. So because these El Niño events tend to occur in boreal winter, then there is upward propagation of these waves into the stratosphere, and then the waves propagate upwards and dissipate, and they affect the polar vortex, weakening the polar vortex and enhancing at the same time the deep branch of the Breward-Dobson circulation. So that means that we have cooling in the tropical stratosphere and warming in the polar stratosphere. So if we think in the potential impact on ozone, as we have a warmer polar stratosphere, then we have less ozone destruction, but then we also have this enhancement of the Breward-Dobson. So we have more polar downwelling, so more transport of ozone from the tropics into the extratropics. So at the end, what we get is more polar ozone in that region during El Niño events. So I would like to illustrate some of these mechanisms with some old figures. And I show you this one from Sassi et al. In 2004. This was when I started to work on this, many years ago. And this illustrates upward wave propagation. These are polar projections in February of temperature to 500 hectopascals, 50, and 3 hectopascals. So at 500 hectopascals, you cannot see very well the continents. Maybe in this figure you see better where North America is, which is the same as in here. So you can see this Pacific North American pattern with an intensification of the Aleutian low here. And then as you go up, you have a wave number 1 pattern that rotates westward with height, which indicates upward propagation. This is also seen in this figure. These are figures from Garcia Herrera et al. 2006. Also with, I didn't say, the figure before was with WACAM 1, as well as these figures here. So here, WACAM 1 shows that during El Niño events, we have enhanced upward propagation. The arrows here are the epiflags. And then the colors are positive divergence, negative divergence. So we have convergence in the area of indicating wave dissipation. And accompanying that wave dissipation, we have an enhancement of the bluebird ocean circulation. That is what is indicated by the arrows here. So the final structure in temperature is the one in zonal mean temperature, is the one in the panel above. That shows the anomalous cooling in the tropics and anomalous warming in the extratropics, reflecting this overturning circulation. And you can also see the typical zonal mean warming in the tropical troposphere, characteristic of El Niño. So in ozone, already Sassi et al. In 2004 discussed the relationship between temperature and polar ozone. And what they did, because at that time WACAM 1 wasn't coupled to the chemistry, was running Mozart 3 with output from WACAM 1 for a few years, 1988 to 1993, yeah? That included a couple of El Niño and La Niña. So we have an El Niño, a La Niña event here and an El Niño event here. And this is polar temperature. So during the La Niña event, we have colder temperatures and we have denitrification there. And the chlorine activates so that at the end we have quite a destruction, lower values of ozone here, green and yellow in this area. While during an El Niño, what we have is, compared to La Niña at least, we have higher temperatures, and then we don't have such a low values of nitric acid, and we have also larger values of ozone for that spring. This relationship between temperature and polar ozone during El Niño events is also quantified by this relationship in Cañazzo et al., who evaluated a few CCN-Val2 models. All these points here are the CCN-Val2 models, and the black is the observations from NIWA. And then you can see how well the observations and most of the models lay in the upper right quadrant, which indicates, these are anomalies, El Niño anomalies of temperature in the polar cap versus ozone anomalies during El Niño, column ozone also in the polar cap. So you can see larger values of temperature with larger values of ozone. Okay, so this is what I explained so far, but then it was reported later that actually these anomalies of the polar vortex and the anomalies in the winds can propagate downwards, facilitated by the role of the stratospheric sudden warmings, and reach the troposphere and even the surface, projecting on a negative Arctic oscillation pattern. And this is seen here. This is from Cañazzo and Mancini. This is zonal mean temperature at the polar cap. At 80 north, and zonal mean wind at 60 north. And you can see the downward propagation of the signal from, let's say, December, January to February, March, and also the winds, how they reach lower levels, reaching the troposphere and even the surface in February, March. This is what Ineson and Scaife also showed in the study comparing their model results with observations. And this is the pattern in SLP, sea level pressure. And you can see that they agree very well with the positive anomalies in the center in the pole and negative anomalies all around, projecting on this negative Arctic oscillation pattern, with implications for surface temperature and precipitation in spring, so that we tend to have warmer and more rainy seasons during El Niño events in Southern Europe, and colder and drier in Northern Europe. And this is only when they used El Niño events with stratospheric sudden warmings. Okay, so this is more or less what we know right now about the canonical effect of El Niño in the stratosphere and its downward propagation into the surface. And as I said before, we have heard about the different El Niño flavors, and in particular about the Eastern Pacific, which is whose SST pattern is presented here, versus the Central Pacific El Niño. So you can see the differences. The larger anomalies occur more towards the east. They reach the coast of South America, while in the Central Pacific we have the anomalies, which are also much lower than for the Eastern Pacific. and they peak in the central Pacific close to the deadline. So this type of event have received a lot of names: deadline El Niño, El Niño Modoki, Central Pacific El Niño, Whirlpool El Niño. I will be using Central Pacific El Niño versus Eastern Pacific El Niño, okay, in the rest of the talk. And the impact of the Central Pacific El Niño events in the southern hemisphere, in the polar stratosphere, seems clear, and the studies that look at that all agree in showing an anomalous warming in the southern hemisphere, in the polar region, as I said. But in the northern hemisphere, the responses are not as clear, and the studies show contradictory results, in the sense that some show anomalous warming or anomalous cooling, or even a non-robust signal. So in this sense, Garfinkel et al. Has a nice paper where they compare the different methodologies that all these studies use, because the problem is, as I said, they use, there are different names for this event with different indices to characterize it. So depending on which index we use, we put different years in the composite. So Garfinkel et al., as I said, compared all these definitions and also the composite sizes, and concluded that actually the signal was in the polar stratosphere in the northern hemisphere was not robust, and depended on the composite size and the definition, the index used to characterize that. So we went back to this a couple of years ago, and we tried to think why this was happening, and then we thought that maybe actually the stratospheric sudden warmings were playing a role in that signal, because depending on which year you put in the composite, you get a positive or a negative signal. Maybe the sudden warmings were masking that response. And I will show you that that's the case, actually. So here, I show you the evolution of the zonal mean temperature at 80 north from October to April versus altitude for all the Eastern Pacific El Niño events of the last 50 years or so. This is reanalysis data. And we get what we already saw, the anomalous warming propagating downwards into the lower stratosphere. Then when we look at the Central Pacific El Niño, we don't get any robust signal, which is also in agreement with previous studies and with Garfinkel results. When we now stratify according to the occurrence of stratospheric sudden warmings, we get something very interesting, I think. For Eastern Pacific El Niño events with sudden warmings and without, we get this warming in the upper stratosphere in both cases. But we only get the downward propagation when we look at Eastern Pacific El Niño events with sudden warmings, which is what previous studies have reported. So that's consistent. For Central Pacific El Niño event, the response with and without sudden warmings is the opposite. And we can see how we have here what we think is the response to sudden warmings in the middle stratosphere. And in this case, we get a robust response for the first time to Central Pacific El Niño events, but only when we don't consider winters with sudden warmings. And we get a robust cooling there. So we extended the analysis, and we look at the different indices that Garfinkel et al. And other papers used, and the composite sizes, etc., and we get the same response. We get, this is all for different indices used to characterize El Niño, the Central Pacific El Niño, and we get nothing. We don't get any response, significant response. When we stratify according to the occurrence of stratospheric sudden warmings, we have the response to what we think is the sudden warming and the robust cooling in the case of sudden warmings with, Eastern Pacific, Central Pacific El Niño without stratospheric sudden warmings. So why do we get this anomalous cooling in the case of Central Pacific El Niño? Here I show you composites for November and December eddy geopotential height anomalies at 500 hectopascals to look at this Aleutian law. So we have Eastern Pacific El Niño with and without sudden warmings, and Central Pacific El Niño with and without sudden warmings. So for the case of Eastern Pacific El Niño, we get the kind of typical PNA pattern. For the case of Central Pacific El Niño, we get opposite responses over the Aleutian low. So we have strengthening of the Aleutian low in the case of Central Pacific El Niño with sudden warmings, and a weakening in the case of Central Pacific El Niño without the stratospheric sudden warmings. And this is also contrary to the feature that appears in Eastern Pacific El Niño without stratospheric sudden warmings, or even regardless of the occurrence of sudden warmings there. So then when we look at the upward propagation of the waves, and this is only wave number 1, well, this is November, December, geopotential height wave number 1 anomalies for Eastern Pacific and Central Pacific El Niño. So we have the anomalies in color, and then the contours are the climatology. So you can see how for the Eastern Pacific El Niño we have a very nice positive interference between the anomalies and the climatology, so that the upward propagation is enhanced. While in the Central Pacific El Niño we have the opposite. We have negative interference, so that we have negative anomalies over a positive climatology, reducing the upward propagation of the waves. That inhibition of the propagation of the waves lead to the stronger polar vortex, less dissipation of waves, stronger polar vortex and colder polar vortex. So these differences between Eastern Pacific and Central Pacific El Niño, they have been also tested not only in reanalysis data, but also in models. And this figure is from the paper that was published this year in Journal of Climate, where we follow this stratospheric pathway in the SIMI-5 models, in 11 high-top models. And this is zonal mean temperature at 80 north for Eastern Pacific and Central Pacific. So you can see how we don't get any robust signal for the Central Pacific, and how when we stratify according to the occurrence of stratospheric sudden warmings, we get opposite responses similar to the reanalysis. And then we also have the warming that doesn't propagate down in Eastern Pacific El Niño without stratospheric sudden warmings. So to summarize this part, I hope I explained that the response of Eastern Pacific El Niño is robust in the northern hemisphere polar stratosphere, such an anomalous warming. The response to Central Pacific El Niño is robust only in the absence of stratospheric sudden warmings, and it shows us an anomalous cooling in this case. And then regarding the teleconnections through the stratosphere into surface climate, Eastern Pacific El Niño anomalies have an impact on surface climate in the Northern Atlantic European region, but there are no evidences of a robust response in this region for Central Pacific El Niño events. So after this summary of our current knowledge of Eastern and Central Pacific events, we go back to the aim of this talk, the 2015-2016 El Niño winter. And what we are going to do is to explore the stratospheric pathway of this El Niño event, its relation to the early final warming and the following surface impacts in the Northern Atlantic European region. So the data that I've used is monthly mean sea surface temperature from the Met Office Hadley Center, then monthly mean and daily mean data from the air reanalysis, and we put the two reanalyses together. This is because at the time of when we started this analysis, it was the only reanalysis that actually provided data for 2016. And the anomalies are computed with respect to the 1981-2010 period. And then we used monthly liquid precipitation totals from the GPCC database. For the method, we need to characterize El Niño event and compare. What I'm going to show you is a comparison with the climatological behavior of Eastern Pacific events and Central Pacific events. So to compute these climatologies, we used for Eastern Pacific El Niño the standardized Niño 3 index from November to February. This is in red the region of the Niño 3, which is more towards the Eastern Pacific. And we take the winters where this index is larger than 0.5 standard deviations and larger than 0.1 times the Niño 4. And then for Central Pacific El Niño, we use the standardized Niño 4 index, which is in yellow there, and you can see that it's more centered in the Central Pacific. And we take the winters when this index is larger than 0.5 standard deviations and larger than 0.1 Niño 3. And in this fashion, we have 6 Eastern Pacific El Niño events and 12 Central Pacific El Niño events. And then what we do is to use these Niño 3 and Niño 4 indices to categorize or to characterize the actual El Niño 15-16. And what we get is that the value of the Niño 3 index was 2.2 standard deviations. And as I said at the beginning of the talk, this is the third largest El Niño event on record. But for the Niño 4 index, we get a value of 1.8 standard deviations, which is record and surpassed by 0.3 standard deviations, the largest Central Pacific El Niño before this one. So even though the community, and we had to categorize the El Niño event as an Eastern Pacific, it had to have some kind of behavior as a Central Pacific as well because of this very large index here. So this makes this event unique in this sense. So we also evaluate sudden warmings using zonal reversals of the zonal mean zonal wind at 10 hectopascals, as in Palmeiro et al. And we use, instead of 60 north, which is the typical definition by Charlton and Polvani, we use the average between 55 and 70 north, although we find the same results actually. And we don't find any sudden warming in that winter. Then when we define also final warmings, when the zonal mean zonal wind does not become positive for 10 days before April 30th, and this leads to an early final warming on March 6th, which we define as an early final warming because it occurred before March 13, which is the 10th percentile of the distribution of onsets of final warmings. And then finally, the statistical significance is addressed with a 1,000 trial Monte Carlo test. So let's start looking at the figures. This one shows just the longitude-latitude distribution of the SSTs for El Niño 15-16 up, and then for the composite of the Eastern Pacific El Niños and the Central Pacific El Niños. So if you compare the three rows, you can see that actually the behavior of the SSTs in 15-16 was a mixture of both. We have these large anomalies in the Eastern Pacific that extend into the coast of South America, but then we also have anomalies here that extend, if you compare with the Eastern Pacific, and we try to plot the deadline. Here you see how the anomalies extend more westward in the 15-16 winter than in the composite of Eastern Pacific El Niño, and resemble more the behavior here of the Central Pacific. That's why when we use the Niño 4 index and the Niño 3 index, we get also these large values in the Niño 4. Then let's look now at the polar response. And this is polar stratospheric temperature. Well, this is zonal mean temperature from 30 south to the pole. December, January, February, March.
Natalia, could you go back to the previous slide just a second? So how do you classify El Niño as a Central Pacific versus an Eastern Pacific? Or are there events that will qualify both as?
No, well, the way we do it, with our methodology, we actually don't have cases that classify in both, because we have this condition that that for being an Eastern Pacific, the Niño 3 index has to be larger than 0.1 times the Niño 4, or the other way around. So in this case, the Niño for 15-16 was an Eastern Pacific because the value 2.2 was larger than the one for the Niño 4 region. So we avoid having cases that belong to both.
But these are fairly subtle differences, huh?
Yeah, I mean, you have, yeah.
And then the other question I had is, when you do Eastern Pacific,
yeah, I forgot to say that.
How does that compare with the conventional N3.4.
So one thing I forgot is that we don't include this event in the composite of the Eastern Pacific. That I didn't say. So this is up to 2015, and doesn't include this event. Okay. The other question is how it compares to Niño 3.4.
Yeah, the standard definition of ENSO being, N3.4 exceeding
I think
standard deviation.
from we didn't look at that. I'm not sure if maybe my students look at that. I don't remember, but from my experience looking at the Niño 3.4 index, it usually looks similar to Niño 3, more similar to Niño 3 than to Niño 4.
Okay.
And also because of all this background on Eastern Pacific, Central Pacific, I'm starting to use more Niño 3 or Niño 4 instead of Niño 3.4.
I mean, certainly your last row brings out clearly the difference between the two. It is small compared to the signaling leader, but it's quite robust.
Mm-hmm. Okay. So in the polar stratosphere, we have colder temperatures from December to February. And then if we compare now with Central Pacific and Eastern Pacific El Niños, I mean, it's pretty obvious what it looks like. So I should highlight that these Central Pacific El Niños do not include sudden warmings, because we showed before that in our study, we reported that actually the signal was robust only in the absence of sudden warmings. That's why we don't mix Central Pacific events with and without sudden warmings. But yeah, this cooling is very similar to this one in the composite of Central Pacific, and is the opposite of what we get for the typical Eastern Pacific event, which is a warming. And then what happened in March is that we get a warming. And actually, I will show you later that that warming is related to the final warming on March 6th. So if we compare now the evolution of temperatures in this first row with the behavior of ozone, we can understand now these low values in January and February related to these colder polar temperatures. And then this peak here in March related to the final warming and the warmer polar stratosphere. And in fact, Manny and Lawrence in their paper said that the timing and intensity of the early final warming and its impact on transport and mixing halted chemical ozone loss. But they don't look at they don't talk at all about El Niño, or they don't relate that cooling or warming or final warming to El Niño. So to try to understand this behavior in temperature, again, we look at upward propagation of waves at the geopotential height of 500 hectopascals, and then if you look at the wave anomalies in colors and the climatology, you can see how in November and December you have, again, this negative interference, so that the inhibition of, the upward propagation is inhibited in early winter, and this is associated with the weakening of the Aleutian low. This is Alaska here, and this is California. So more or less this area could reflect the behavior of the Aleutian low. So we have a positive anomaly here, so that the low is weaker than the climatological behavior. So this is all very similar to the behavior that we reported for Central Pacific events. Now let's go back to the final warming in March. So I'm not going to show it, but actually when we look at the daily evolution of the temperatures, we do see that the warming, even though here we plotted monthly means, the warming starts on March 6th. We don't see that before there. And then here I plot this is the northern annular mode evolution around the onset of the final warming. So we have negative values in the stratosphere, and you can see how the signal propagates down and affects the surface a few weeks after the event. If you compare with the composite of sudden warmings, it is in fact pretty similar, and there are a few studies that reported impact of early final warmings on troposphere and surface climate. But if we compare with all the final warmings, then we do see some negative anomalies in the stratosphere, but we don't see such a troposphere-stratosphere coupling. Then, to kind of try to attribute or try to understand the relationship of between the final warming and the Central Pacific El Niño, we plotted the composite of early final warmings with Central Pacific El Niño. And you can see again, we only have 4 cases. So maybe it would be nice actually to look at this in long model simulations, but still at least what these 4 cases indicate is that the pattern is similar to the one that occurred in 2016. So the frequency of occurrence, even though the record is very short, we found 4 early final warmings with Central Pacific El Niño and 1 with Eastern Pacific El Niño. So maybe this might suggest that Central Pacific El Niño are more prone to have early final warmings.
What was your definition of early?
Before the 10th percentile, so before March 13th.
Days, yeah.
Okay, and then, yeah.
Can you just describe how you built those composites? Like, what's the central date? Those are here. How did you line them up?
So it's the onset of the early final warming.
At 10 hectopascals or what?
Yeah, we define the final warming in, at 10 hectopascals.
All the way at 10 hectopascals.
Yeah, when the zonal mean zonal wind does not become positive for 10 days before 30th of April at 10 hectopascals. But in the average 55 north, 70 north instead of 60. But I believe the results didn't change. I seem to remember. Okay, so finally, I want to show you the impact on tropospheric climate. And these are March, April, May, geopotential height values for the El Niño 2015-16. These are the contours, and then the colors are precipitation. And then on the right, we have blocking frequency. So what you can see is that we have a lower values of geopotential height around, the minimum is around 45. That means that the storm tracks are shifted down compared to the typical climatological value, and that is associated with large precipitation in Southern Europe and the Mediterranean region. As I said before, we had values that exceeded the 95th percentile of the spring totals in West Iberia and in the Balkans. And then we have this high value of geopotential height, which is associated with blocking frequency in Greenland. And there are a few papers that report the influence of, or the association of blocking in this region with negative values of NAM in the stratosphere, and also with this shift of the storm tracks south and the increased precipitation in Southern Europe. Finally, we compare these composites with the similar ones for, these are not composites, these are for only 2015-16. And we compare them with the composites for Central Pacific El Niño with early final warmings. And you can see that the similarities are good. So we have the low values of geopotential height, and then larger precipitation in the south of Europe, and the higher blocking frequency over Greenland. Okay, so just to conclude, I'll summarize the main results. So despite being cataloged as an Eastern Pacific El Niño, I hope I have convinced you that at least this El Niño event showed several signatures that were characteristic of the Central Pacific El Niño events, leading to an unusual event on the observational record. So we get record SST's anomalies in the Central Pacific El Niño region. Then the stratospheric response in the Northern Hemisphere was CPEN El Niño-like, with a weaker Aleutian low in early winter and a midwinter polar cooling, which is the opposite to the behavior expected for Eastern Pacific El Niños. Then we have an extremely early final warming on March 6, which led to a weakening of the polar vortex. And with the short record, early final warming seems to be more prone to occur during Central Pacific winters than Eastern Pacific winters. The early final warming during Central Pacific El Niño winters seemed to induce persistent Greenland blocking that caused above normal precipitation over Southern Europe and the Mediterranean in the spring of 2016. And then finally, we provide the first evidence that Central Pacific El Niño event, together with early final warmings, have notable effects over the North Atlantic European sector in late winter and spring, which might have implications for seasonal predictability. And with this, I've finished. I hope you enjoyed the talk, and I want to thank you for your attention. The main results of this talk are in these three papers. The first one talks about the Niño 1516, and the other two talk about the differences between Eastern Pacific, Central Pacific.
Hello? Questions?
I have a question. So you said there were 4 examples of Central Pacific El Niño with early final warmings.
Versus one. Versus one with...
Versus one in Eastern Pacific. And so out of all of the Central Pacific El Niños, what percentage do these 4 cases represent? I mean, you have a record from 179 to present or something like that?
No, from 59, and we had 12 events, so 4 out of 12.
4 of the 12 Central Pacific El Niños are accompanied by early final warmings. Okay, and you interpret that in the sense that Central Pacific El Niños tend to suppress or to interfere destructively with the climatological wave activity, at least in early winter. So that tends to suppress sudden warmings, which, as you also have shown, tend to muddy up the waters. I mean, they are almost like noise in the system. So that then when the final warming comes, it can be early. Because, and it can come
actually I think I read there is a reference by Hu et al., I think, that showed that usually...
That's the story.
Yeah, and this is the upward propagation for El Niño 1516. You can see how in January and February this changes and it starts to look like positive.
So now I have only one other question. What was 2012, 2013 in terms of...
we didn't look at
2013 was a very wet spring in Southern Europe.
Yeah, there was no...
I was there, so I know.
So, I don't know about the Central Pacific Index there.
Natalia, nice talk.
Thanks.
Was this accompanied in March or after March with an increase in tropospheric ozone at higher latitudes?
I don't know. I don't know if anybody...
Look at, that's the question of to what extent does these events
affect
influence the budget of...
Because you would, if it's gone up and there's an increase in ozone, then downward transport, then
something that
might be interesting.
I don't know much about tropospheric ozone, or I know almost nothing, but it's true that something that I'm interested in is in knowing if, like, when there are El Niño events and you have this enhancement of the bluebird ocean circulation, for instance, for the canonical Eastern Pacific, then you get this downwelling, and I don't know up to what point this transport of ozone can reach the troposphere. So that's something I'm interested in, but we never look at that. Actually, maybe now with Marta, that she's going to be in Spain, maybe we're talking about maybe looking at that.
So if this actually had something to do with the interrupted QBO, what would be the mechanism and which direction would it go? Is the INSO affecting the QBO or vice versa?
Well, I was talking a little bit with Rolando about this because I know about the QBO, but I didn't read the papers until this morning. So I read the 3 papers that I know, and then it's true. And then I was thinking that I don't know why nobody looked at the relationship with El Niño, because you can think that El Niño triggers waves that go up and affect the QBO, and there are a couple of papers that showed that, I don't remember which of the phases affect, but even many years ago, it never got published, but I looked in the ECA model at how with simulations of El Niño 97, 98, how that affect the QBO phase, and I think it shortened the westerly phase during those type of El Niños, so there might be some relationship there. On the other hand, I know that the QBO can affect convection and can affect also, the QBO can affect convection and can affect maybe generation of El Niño or something, I don't know. But I think, the first thing I would look is to see if actually how is the convection during Central Pacific El Niño, which I know, even though the anomalies in the SSTs are much lower, I know they are very efficient to generate waves and generate convection because of the region where they occur. So I would look at how the waves are and how they affect the QBO.
So I have a comment on that if you want to hear it.
Yes.
Which is in WACOM, we only have one simulation where we have to hit the atmosphere pretty hard to produce interrupted events. And invariably, those happen in Northern Hemisphere spring, February, March time period. So that seems to be something that they have in common. And so I would guess that if you have a large wave event generated at the right time, and the westerlies happen to be in the right place at that particular time, then you can interrupt them. But it doesn't happen in our normal WACOM simulations. So when we run the present period from 75 to 2015, we get 0 interrupted events.
I don't know. I would like to see how the Central Pacific events are there, because this one, according to the Niño 4 index, it was 0.3 standard deviations larger than the
Right, this was a large event.
So I don't know how many more you can get in a normal simulation.
But, still this interrupted QBO event looks to me like a black swan, and it may have had something to do with this particular answer, but you had another 3 early sudden warmings, which didn't interrupt anything on the QBO. So.
Yeah. Mm-hmm.
I'll just add 2 cents worth. Since Peter Hitchcock's not here, he's right behind. Here, Peter, what do you think?
Yeah, I'm sorry.
So I looked a bunch at the disrupted QBO in idealized models, and my sense, I think overall I would agree with what Orlando says, is that you need a sort of pathway for the wave activity to get into the QBO. What caused the disruption of the QBO was waves coming in from the side as opposed to vertically generated by convection, okay, which is rather different from the regular mechanisms for the QBO. Yes. That being said, I still think ENSO could be quite relevant for it in sort of forming this bridge of the westerlies to get the waves in there. But I still think you need a rather big kick to come along to start it out. It would be interesting to know whether that kind of a meridional propagation of waves could come about from Central Pacific El Niños. And I don't have a sense of that, but there's a bunch of things that have to be right in the stratosphere before the QBO is susceptible to that kind of a disruption, I think.
I'm sorry I missed your talk in Portland.
It's okay.
So you probably said this and I missed it, but I wasn't sure how anomalies were being defined. So for the case of the Central Pacific with no sudden warmings, was that relative to neutral years with no sudden warmings or all years?
That's the key question. So it was, the anomalies were computed with respect to all the years, with and without. And then we had the concern, like, maybe we had the opposite responses because we have, like, we are biasing our climatology towards. But we did it with anomalies with respect to each own composite. So for the case of Central Pacific El Niño with sudden warmings, we used only winters with sudden warmings to compute anomalies, and the other way, and the results didn't change.
Thanks.
Okay, let's thank Natalia again.
Well, thank you.